It is Monday morning. You spent the entire weekend building this project.
Oh yeah, the classic weekend sprint.
Right. You built an AI agent, you wired it all up, and it works flawlessly. I mean, it remembers context, it executes tool calls perfectly.
You demo it, and everyone is just completely amazed.
Exactly. But then your first real user logs in, and they type this brutally simple prompt, something like, rename Ember to Infernia.
And we all know what happens next.
Instantly, your beautiful creation just completely breaks. It enters this infinite loop, calls the exact same rename tool like 15 times in a row.
Burning through, what, $20 of API credits in 2 minutes?
Yeah, and then it finally just crashes with an out-of-memory error.
It is the ultimate Monday morning reality check. That illusion just breaks, and you suddenly realize, well, you haven't actually built a production agent.
You've just built a really impressive prototype.
Right, exactly.
So today we are doing a deep dive into the leaked code of Claude Code, along with this fascinating piece of analysis by Harrison Gual.
Titled, The 90% Problem, Why Most AI Agents Are Still Broken.
Yes. And our mission for this deep dive is to figure out exactly how you, the developer listening right now, should be prioritizing your build time when you're architecting these systems.
Because the instinct for a lot of developers when they see that infinite loop on Monday morning is just to blame the AI.
The model just isn't smart enough yet.
Right, so they wait for a newer release, or they swap out their endpoint for some heavier, more expensive model.
But the source material we have today makes it very clear that's the wrong move. We're focusing heavily on two non-negotiable takeaways here. First, prioritizing context management above everything else.
And second, actively closing every single feedback loop.
Yeah. And Guai's analysis actually uses hard production data to prove that chasing those model upgrades is basically a trap.
It really is. The failure almost never actually lies with the model itself.
I want to frame this with an analogy that I think maps a bit closer to how we actually build software.
Okay, let's hear it.
Relying entirely on the LLM to make your agent work is kind of like buying the most expensive, top-of-the-line Formula One engine.
But dropping it into a soapbox doobie car.
Yes, exactly. Or like plugging it into a motherboard from 2005 with a completely bottlenecked data bus.
Right, the engine is incredibly powerful.
It's capable of billions of calculations a second. But if the surrounding architecture, the steering, the brakes, the data delivery, can't handle things when they go wrong, that processing power is entirely wasted.
You're just going to crash at really high speeds, and that maps perfectly to the core thesis here.
The 90% problem.
Yeah. Guo argues that building the agent that simply functions, getting the engine to turn on, is actually the easy part.
The 10%.
Right. Building the surrounding architecture so it doesn't just spontaneously crash under real-world loads, that is 90% of the actual work.
So to figure out where those crashes actually happen, we first have to understand the anatomy of an agent.
Which the source breaks down into the 5 pillars of production agents.
Okay, let's list those out.
You've got context management, memory management, reflection planning, and tool use.
Now, reading the text, it makes this really sharp distinction between those pillars. Like, developers don't need to spend equal time on all 5.
No, definitely not. There is a massive divide in how these pillars actually scale in the real world.
Because some of them just kind of take care of themselves now.
Exactly. Planning and tool use, for instance, are increasingly solved problems right out of the box.
Because they ride on the model improvements.
Right. If you look at newer models, like, say, Claude Opus 4.6, they have been heavily fine-tuned on JSON schemas and function calling.
So the model inherently understands how to use a tool.
Its internal attention mechanisms are already optimized to know exactly when and how to trigger it. You essentially get that reliability for free just by routing to a newer API endpoint.
Okay, so the model handles the syntax, the execution gets better. But that leaves context management and memory management.
Which the source flags as the absolute primary failure points. They are pure engineering problems.
Right, not model problems.
Yeah.
But I want to push back on this slightly, or, play devil's advocate for the listener here.
Sure, go ahead.
When we talk about context management, the standard developer approach is usually pretty straightforward.
You mean just grabbing the history?
Yeah. You take the user's prompt, you append the last, 10 messages from the chat history, and you just throw that payload at the API.
Right.
Why is that considered such a massive, insurmountable engineering bottleneck?
Well, because that approach assumes the model processes all text equally. And that is just not how attention mechanisms work at scale.
Because of the noise.
Exactly. If you just dump a massive uncompressed chat log into the API, you introduce a ton of noise. The model's attention gets diluted by completely irrelevant entities.
Oh, that's the lost in the middle phenomenon people talk about.
Precisely. But more importantly, treating context as just like a simple string concatenation completely ignores what Grow calls the LLM versus code divide.
Okay, break that down for me.
Well, production agents don't just make one giant call to the AI.
Right, they break the workload into different operations based on compute costs and latency.
Exactly. The architecture relies on three very distinct patterns. First, you have direct side queries.
Like asking a quick question.
Yeah, your code asks the LLM a very narrow question like classifying a user's intent, and it gets an answer in maybe 250 milliseconds.
Okay, stateless and fast.
Mm-hmm.
Makes sense.
Right. Second, you have forked subagents. So say a user asks the agent to summarize a 50-page PDF.
You definitely do not want to load that entire PDF into your main conversational context window.
No, that would be a disaster. Instead, your code spins up a subagent, hands it the document, totally isolates its context, and just waits for the summary.
So the main loop stays clean.
Exactly. The main loop is that third pattern, and it's the core engine. It manages the tools and the ongoing interaction.
Which means if your strategy is just throw the last 10 messages at the model, you're doing it wrong.
You are polluting the main loop with massive amounts of irrelevant state data.
Wow, okay.
The orchestration, the deterministic code that decides what specific tokens the model actually sees and when it sees them, that is the actual engineering challenge.
Okay, so if context routing is the true bottleneck, that fundamentally changes where a developer should be spending their time on the weekend.
Completely changes it.
We really need to talk about this leaked data from Claude Code then, because the disparity in that code base is just staggering.
Oh, the line counts. Yeah, it's wild.
The leaked repository is roughly, 512,000 lines of code?
Yep, over 500,000 lines.
But the actual heart of the agent, that wild true loop inside QueryDot that handles the core LLM interaction,
It's tiny.
it's only 1,421 lines long.
It is a tiny fraction. It represents maybe like 0.25% of the total project.
So what are the other 500,000 lines doing?
They visualize the 90% problem perfectly.
Hmm.
A huge portion of that surrounding code is dedicated exclusively to grooming the data before it ever even reaches the LLM.
Right. For instance, the source notes there are almost 4,000 lines of code dedicated strictly to the context management pipeline.
Almost 3 times the size of the core loop.
Let's unpack those 4,000 lines,
Mm-hmm.
because the source mentions this 5-level progressive compression pipeline.
Right.
To me, that sounds a lot like triage packing for a long trip.
Yeah.
You don't just shove everything into a suitcase.
No, you'd never get it zipped.
Right. First, you fold the clothes to save space. Then maybe you roll them.
Yeah, that's a highly accurate way to look at it. The code is dynamically triaging tokens.
So what does level 1 look like?
Level 1 might just be summarizing older conversational turns, getting the gist of what was said 10 minutes ago.
Okay, and if the bag is still too full?
Then you move to level 2, which might involve stripping out heavy metadata or like raw JSON responses from previous tool calls that just aren't strictly necessary anymore.
So you're actively throwing out the shirts you wore 3 days ago.
Exactly. And by the time you reach level 5, the code is aggressively dropping even non-essential system prompts.
Oh, wow. Just to ensure the critical instructions remain right at the forefront of the model's attention window?
Exactly. You have to keep the signal-to-noise ratio pristine.
The source also mentions micro-compact dual code paths, depending on the cache state. I assume this ties directly into prompt caching economics.
It absolutely does. Modern APIs let you cache certain prefixes of your prompt.
To save money and reduce latency, right?
Right. And the Claude Code architecture actually has parallel logic paths for this.
How did that work?
Well, if the code detects that a specific chunk of context is already hot in the server's VRAM, it routes the request through a path optimized for that specific cached state.
Oh, that's clever. And if it's not,
If it's a cold start, it routes it through a completely different, much more aggressively compressed path.
they even built a local system for estimating token counts without making an API call, didn't they?
They did. It maintains less than a 5% error rate, purely to optimize this routing logic without adding API latency.
The stakes for getting this plumbing right are just incredibly high. There's this detail in Guo's breakdown about a circuit breaker mechanism that really underscores the cost of failure here.
Oh, the 3-strike rule.
Yeah. The code enforces a hard stop if the agent fails 3 consecutive times. It literally breaks the circuit and halts execution.
Which sounds drastic, but they had to build it.
Because without it, confused agents that got caught in infinite loops were burning through 250,000 wasted API calls a day.
250,000 calls, just absolute garbage generation.
That is the financial cost of poor orchestration.
And it brings us right back to why fixing your context is a much higher priority than upgrading your model.
Right, because the model isn't the one causing the loop.
Exactly. Guo actually ran production A/B evaluations to prove this hierarchy.
What were the numbers on that?
He took an agent that was failing in production. It had a pretty dismal 40% pass rate.
Okay, not great.
He kept the exact same LLM, didn't upgrade it at all, and just implemented 8 specific fixes to the context and orchestration pipeline.
I really want to highlight the mechanics of those fixes, because out of the 8, 7 of them were pure code with 0 additional LLM cost.
Pure deterministic engineering.
Like the structured error classification. I love this one.
It's so elegant.
Instead of taking a raw Python stack trace and just blindly feeding it back to the model, which is dense, it's noisy, it confuses the attention mechanism.
Right, the model panics when it sees all that garbage.
Exactly. The surrounding code parses that stack trace first, and then hands the LLM a clean, structured JSON error, like just file not found at path X.
It is all about reducing the cognitive load on the model.
Yeah. Were there other pure code fixes?
Oh yeah, enforcing strict round limits was another one, which acts as like a secondary circuit breaker.
But the most impactful change, the text says, was the only one that actually added any API cost.
The pre-loop planning step. And it cost a massive 0.003 per request.
0.3 of a cent. That's nothing. Why does a pre-loop plan work so well? Is it because LLMs are fundamentally next token predictors?
Exactly that. By forcing the model to write out a step-by-step plan before it executes a tool call, you are forcing its internal state to map out the logic sequentially.
Oh, I see. So when it finally generates the tool called JSON.
Its attention heads are actively referencing the logical plan it literally just wrote out on the previous lines.
Which drastically reduces hallucinations.
Precisely. And the outcome of just those orchestration tweaks was massive. The pass rate jumped from 40% to 60%.
With the exact same AI model.
The model was always capable of completing the task. The unrefined context was just dragging it down.
Okay, so this establishes the first major rule for your build time. You have to construct the data bus before you buy the CPU. Fix your context management.
#1 priority.
But getting pristine data into the model only really solves half the equation, right?
Right.
What happens when the agent acts on that perfect context, calls a tool, and then still makes a mistake?
Because it will happen.
Always. And that brings us to the second mandate from the source material, closing every single feedback loop.
This really requires a huge shift in how developers view error handling.
How so?
Well, the text highlights this pervasive issue where developers confuse features existing with loops being closed.
Ah, having a half-built infrastructure.
Exactly. It gives teams this false sense of security.
Let me relate this to traditional software engineering for the listener.
Yeah.
An open loop is basically a try-catch block that catches an exception, prints error occurred to the standard output log, and then just lets the function return a null value.
And the program just breaks downstream anyway.
Right. Or, to use a real-world analogy, an open loop is like a smoke alarm that just beeps and logs that there's a fire.
It tells you you're in trouble, but it doesn't help.
Exactly. A closed loop is a sprinkler system. It senses the fire, sprays the water, checks if the fire is actually out, and if not, it sprays more water.
You don't just want a log, you want the fire put out before the user ever even sees it.
That is the exact distinction. Does the text give any examples of this?
Yeah, Guo contrasts several prominent open source agents with production-ready systems to illustrate this perfectly.
Like which ones?
If you look at open source projects like OpenClaw or Hermes, they boast incredibly impressive features.
They sound great on paper.
They do. They utilize SQLite databases for memory. They implement full text search. They have dual-layer markdown storage. I mean, the features absolutely exist.
The databases are running.
But their operational loops are frequently totally disconnected.
Meaning what exactly?
Well, they might have a verification step that checks if a database retrieval was successful. But if that retrieval fails, the code often just logs the failure and allows the agent to proceed to the generation step anyway.
Oh, that's terrible. So the agent then just hallucinates an answer based on empty context.
Yes, and the user receives a completely broken output.
So the standard for a closed loop requires the system to actively intercept the failure, use the failure itself as feedback, and self-correct automatically.
Yes. And the source provides this brilliant example of this from Claude Code's memory architecture.
Oh, the background extraction agent.
Yeah. They were running this sub-agent whose sole job was to quietly pull persistent memories out of the user's chat history.
Sounds useful.
It is, but in early evaluations, its success score was literally 0 out of 2. It was completely failing to extract the right entities.
So how did they fix it without just waiting for a better model?
They added what they call trust verification. They finally closed the loop.
How does trust verification work in code?
The code takes the entity that the subagent extracted, and it feeds it into a super lightweight verification prompt. Just asking, did this extraction capture the exact entity requested by the user?
Okay, and if it says no?
If the verification fails, the code takes that failure reason, appends it to the subagent's prompt, and literally forces it to retry.
It's essentially just an if statement and a recursive API call.
That's all it is.
Right.
But by implementing that simple closed loop, the evil score jumped from 0 to a perfect 3 out of 3.
It is such a conceptually simple software pattern, but it represents the hardest 10% of that 90% orchestration problem.
Right. The value isn't in building a massive SQLite database.
Well,
The value is in the meticulous, tedious wiring required to ensure that when a query to that database fails, the system catches it, reasons about the failure, and tries a different query autonomously.
so if you are a developer sitting in front of your IDE right now, getting ready to build or refactor an AI agent, your action plan really needs to reflect this reality.
Absolutely. First, you have to measure your current model's baseline performance before you change anything.
Right, you cannot improve what you aren't evaluating.
And second, please stop relying on API endpoints to solve your architectural flaws.
Budget 90% of your build time for the 90% problem. Writing the basic agent loop that calls a tool, that is a weekend project.
Anyone can do it.
But the error handling, the progressive compression pipelines, the memory lifecycle, the deterministic routing, that is the actual product.
That's what you're really selling.
You have to prioritize context management to ensure clean input and relentlessly close every feedback loop to ensure reliable output.
It really is a paradigm shift for the industry. We are constantly trained by social media and developer blogs to obsess over the latest LLM benchmarks.
Like, oh, look at the new reasoning scores.
Exactly. But Harrison Gore's analysis flips that narrative entirely. The AI model itself is basically becoming a commodity.
It's just raw, interchangeable electricity.
Right. The complex engineering surrounding it, the circuit breakers, the routing logic, the retry mechanisms, that is where the real intellectual property lies now.
It makes you wonder about the future trajectory of the whole field, honestly.
How so?
Well, think about it. If the model is just a commodity that you rent by the API call, and the true reliability of the system relies on progressive compression pipelines and robust exception handling,
Yeah.
does that mean the most valuable AI developers of the next decade won't actually be AI researchers at all?
Oh, that's an interesting thought.
Will the true heavyweights in this space just be the most meticulous, detail-obsessed, traditional software engineers who know how to build unbreakable deterministic systems?
The people who know how to write the 4,000 lines of plumbing.
Exactly. So as you look at your own code base today, take a hard look at the architecture. How much of your code is dedicated to simply calling the shiny new engine, and how much of it is the unglamorous, absolutely necessary plumbing required to keep it from burning down on Monday morning?